In our last class, we spoke about the equilibrium constant as something that is unique first and foremost to every chemical reaction that can exist in a state of dynamic equilibrium with its products. And also we spoke about how to develop what we call the Kc expression. Now, the Kc expression, development of the Kc expression is extremely important for what we want to move on to in this class, and that is using the Kc expression and information about the concentrations of every species in that system at equilibrium in order to calculate the actual value of Kc. Now, just before we go into the calculations themselves, what is Kc? If we write out a Kc expression and then we fill in all the various different equilibrium concentrations, what is Kc? And I suppose the easiest way to talk about Kc is a measure of progress. Okay, now progress meaning how far the forward reaction has managed to go. So therefore, if you end up calculating a large Kc value, that means that the reaction has progressed quite well to the right, that it favors the products. Okay, if you get quite a small Kc reading, well then that means that that the reaction hasn't proceeded very well. And if you get a Kc value that is less than 1, so if you get a fractional 1, 0.5, a half, 7/8, whatever it's going to be, anything less than 1, that favors the reactants. So therefore we could say that, you know, the reaction has not proceeded very well if the Kc value is small. So therefore, just in a nutshell, what is Kc? It's a measure of how well the reaction has proceeded towards products. Okay, and as we said already, because in this part of the world we read from left to right, the left to right equation is always one to be considered to be the forward reaction. So Kc, as I said already, it's simply a measure of how much the reaction has proceeded towards the right hand side. It is dependent on temperature. Now, just to be very careful here, Kc has a given value for a given temperature. So therefore, changes in temperature will affect Kc, but changes in pressure won't. And I need you to just think about that very carefully. Because Kc is dependent on temperature, only temperature can change its value. Okay? Yes, we know that pressure is a stress in terms of equilibrium, but keep in mind that when we're simply altering the position of equilibrium, we're going back to equilibrium. So therefore the Kc value will be the same. Okay? So the only thing that can change Kc as far as the stresses that we've studied so far is temperature. Pressure is not going to affect the Kc value. Yes, it will affect the position of equilibrium, but no, it won't affect the value of Kc. Units of Kc we talked about the last day too, and they'll depend on the reaction. Okay? Every species in the system is measured in moles per litre. So when you form your Kc fraction, all you've got to do is see how many of those units moles per litre you can cancel. And then the ones that are excess, whether they be on top or the bottom, they are the units that are left for your answer. Sometimes there are no units, sometimes they cancel altogether. The reverse reaction will have what we call the inverse or the reciprocal of the original Kc value. So for example, if the forward reaction has a Kc value of 4, then the backward reaction will have a Kc value of 1/4. If the forward reaction is 60, the backward reaction is 1/60th, and that makes perfect sense. Think about it. If the forward reaction is a Kc value of 60, then that's very much in favour of products. So why would the system want to go back to reactants? If they're favouring products, they're favouring moving towards the right hand side, which means the reciprocal of 60, 1/60, will represent Kc going back, which is very small. So therefore the favour is still, if you want to put it that way, in favour of the products of the forward reaction. Okay, what else about Kc? Well, just to take a look at a given chemical reaction, very simple one. H2 plus I2 exists in a state of dynamic equilibrium with 2Hi. It's 46 at 458 degrees Celsius. Now, what can change that value is a change in temperature, not a change in pressure. Okay, even if the values or the volumes are different either side, pressure won't affect the value of Kc. Okay. Secondly, if I reverse the reaction, as we said already, if the forward reaction is 46, then the backward reaction at the same temperature will have the reciprocal of the forward reaction. So if the forward reaction is 46, this way here, then the backward reaction is 1/46, the reciprocal of the forward reaction. What about if we change the coefficients? Now, in this situation here, I'm just halving them. So it's a half H2 plus a half I2 exists in dynamic equilibrium with Hi. But I need you to remember that the coefficients, when you put them into Kc, become the powers. So what was up here, originally a power of 1, and power of 2, has become the power of a half. Now, the power of a half in mathematics is better known as the square root. So if you have your reaction halved, like that, well then you will have a Kc value of the square root of 46. If you have a third, then it will be the cubed root. If, for example, the coefficients were quartered, then the Kc value would be the fourth root, and so on. Okay, and that just again reinforces from a mathematical point of view that fractional indices have a corresponding root. So, for example, the power of a fifth is the fifth root, the power of a half is the square root, and so on. So just keep in mind, if you reduce the coefficients through division of 2, 3, 4, 5, or whatever, well then you're going to have to bring in the root in relation to the Kc value that represents the fraction. So if the fraction is a half, if you're halving all the coefficients, square root. If you're thirding all the coefficients, cubed root. If you're getting a quarter of all the coefficients, fourth root, and so on. Notice temperature doesn't change. We've got to do these things at constant temperature to make sure we're measuring just Kc, because temperature is something that affects the value, I should say, of Kc. Okay, now I'm going to move into the calculations, and I'm going to do plenty of examples in this class, so please bear with me. You can pause as frequently as you want. I'm going to do at least 5, because there are tiny little things we've got to change from question to question to make sure we have the whole thing covered. In order to calculate the numeric value of Kc, there are 2 things that we need to know. First of all, we must be given the balanced equation. That has to be present, okay? Because from the balanced equation comes the Kc expression. So that's going to be the very first thing you'll always do in a question like this. Look for the balanced equation, write down what Kc is in terms of the balanced equation, and then secondly, through mathematics, simple mathematics, work out what is the concentration of every species at equilibrium. Not at the beginning, but at equilibrium. When the system has settled down and reached what we would say a state of dynamic equilibrium, you need to know what the concentrations are, you know. And some people will say, well, how would you determine the concentrations at equilibrium? Simple, titration. If you want to work out what concentration of HCl you have at equilibrium, okay, you titrate it with a standard solution of NaOH. So just keep that in mind. To get the concentrations at equilibrium, we can always carry out a simple titration. And they may ask that, they may not. I haven't seen it too frequently asked, but just be in the back of your head, that's how we get the concentrations. Okay, so they're the 2 things we need starting any question. Number 1, we need a balanced equation to write Kc. And number 2, we need to work out the concentrations of every species at equilibrium. Now, how do we do that? Well, first of all, you write down the equilibrium constant expression Kc for the given reaction. Okay, then we must determine the molar concentration. Now, this is important because the molar concentration can only be used when you give it, as the name suggests, in moles per litre. Now, say for example that the system is a 10-litre container. Well, then the concentrations at equilibrium are going to be moles per 10 litre because that's the size of the system. So when they mention the size of the system, then you must always make sure that your concentrations at equilibrium are divided by the size of the container in order to make sure that the concentrations going into Kc are moles per litre. And then what do we do when we get the concentrations of every species at moles per litre? We substitute them into Kc. You get out your calculator and you do what the figures tell you to do. You multiply the numerators, you multiply the denominators, you divide the denominator into the numerator, you get your value, and then, if you can, work out what units are in excess, top or bottom. Okay, so there's nothing like the examples. I'm going to go through this with you, and I'm going to take these in kind of gradations of difficulty, just adding a little bit more in each time we move through various different questions. When we come across a question that I'm going to ask you to do yourselves, just pause the video. Pause it, try and do it, and the solution will follow immediately. Okay, so worked example, this is on page 275 of your textbook. It's worked example 17.3, so that means it's actually worked out in your book as well. The reaction, nitrogen plus hydrogen, sets up dynamic equilibrium with ammonia, was allowed to reach equilibrium at 450 in a 1 litre container. Now that's nice. A 1 litre container means that all the concentrations at equilibrium will automatically be in moles per litre, so I don't have to worry about dividing by the volume of the container. It was found that there were 13.6 moles of nitrogen, 1 mole of hydrogen, and 1.5 moles of NH3 in the container when equilibrium had been established. Now that is the key position. We only need to know the concentrations at equilibrium, all right? So calculate the value of Kc at this temperature. Take the 3 steps. Number 1, we write out the Kc expression. And please remember what the Kc expression is. It's the concentration of the products, NH3, raised to the power of the coefficient of NH3 over the concentration of nitrogen, raised to the power of its coefficient, which is 1, multiplied by the concentration of hydrogen, raised to the power of its coefficient, which is 3. Now, notice there's square brackets in the Kc expression. That's vital, because the square brackets mean moles per litre. Okay? What we now do is we take the concentrations that are present at equilibrium and simply feed them in. So let's take a look and see. We're told there's 1.5 moles of ammonia in a 1 litre container. So that's moles per litre. So that's exactly what I require. So it's 1.5, notice the change in brackets, squared, over the concentration of nitrogen, 13.6 moles in a 1 litre container. So that's 13.6 raised to the power of 1, multiplied by the concentration of hydrogen, which is 1 mole per litre, raised to the power of 3. And all I do then is I reach for my trusty calculator and I turn on my fraction. So fraction on, 1.5 squared on the top, and then 13.6 multiplied by 1, which is 13.6, and then we do the division, and we end up getting in decimal form 0.1654. Tiny. So therefore this does not really favour products, this favours reactants more so. And we kind of know that with ammonia. Ammonia is difficult to push forward. But there's your Kc value. Now, what are your units? What have I got on the top? On the top I have moles per litre multiplied by moles per litre, because that's what moles per litre squared means. On the bottom I have moles per litre for the 13.6, and then I've got moles per litre cubed. So that's 3 of them, just to show you what I mean by this. Okay, so where's the excess? That goes in there once. That goes in there once and in there once, meaning that the units of this thing are 1 over moles per litre squared. Moles per litre squared. That's it. So that's, if you want to put the units in, that's how you do the units. Okay, so fairly straightforward question. Now, for Leaving Cert Honours, they're not going to give you equilibrium concentrations. They're going to ask you to find them. So let's take the next question. 17.5, page 280. 1 mole of hydrogen iodide was injected into a 1 litre flask. So please make sure you understand it's a 1 litre flask, so therefore we don't have to divide by the volume of the container. The following equilibrium was set up. It was found that 0.8 moles of hydrogen iodide were present at equilibrium. Calculate the value of Kc. Now again, the first thing I want to do here is to write down the Kc expression. And the Kc expression is the concentration of iodine multiplied by the concentration of hydrogen over the concentration of hydrogen iodide squared. So in other words, concentration of iodine multiplied by the concentration of hydrogen, that's your numerator, and your denominator then will be the concentration of hydrogen iodide squared. So always write that down first. Now we've got a problem. 1 mole was injected. That's the beginning. It was found that 0.8 moles of hydrogen iodide were present at equilibrium. Brilliant. But what about the other two? What's the concentration of hydrogen and iodine? So what I would suggest going forward is that you follow what I'm about to do here. Okay, follow this setup, and it's kind of like a table setup. So there are 3 things we've got to look at. What were the concentrations at the start? What was the change in the concentration as we moved towards equilibrium? Okay, now this will make sense in a moment. So first of all, we have 3 species. So 1, 2, and 3. The first species is Hi, the second species is H2, and the third species is I2. Now, let's take a quick look at this. What are we told in terms of the concentrations at the beginning? At the beginning, we're told 1 mole of hydrogen iodide was injected into a 1 litre flask. So at the start, 1 mole of hydrogen iodide was injected. Now, at the beginning of every chemical reaction, there are always reactants and never products. At the very, very start, you've got your reactants, but you don't have any products. That's the start of any chemical reaction. Okay, and then what are we told? It was found that 0.8 moles of hydrogen iodide were present at equilibrium. So down to the equilibrium line, we put in 0.8 for the HI. That's the number of moles present at equilibrium. Now, the rest of this can be filled in. Watch. First of all, if I started with 1 mole of hydrogen iodide and I reduced down to 0.8, the change is I have used up 0.2. Okay, that's the change. That's very simple maths. The change, now this is key. The change line, this one here, the ratio must be the same as the balanced equation. Okay, balanced equation. Now what does that mean? Well, if the balanced equation is 2:1:1, then the change must be in the same ratio. 2:1:1, meaning 0.1 and 0.1. Now because H2 and I2 are products, they are created as we move towards equilibrium. So therefore now we just tally the columns. 1 minus 0.2 is 0.8, 0 plus 0.1 is 0.1, and 0 plus 0.1 is 0.1. And they happen to be the concentrations that I want to put into Kc, because they are the concentration in moles per litre at equilibrium. Okay, now how do I know they're moles per litre? Well, they're moles. And check the size of the container, 1 litre. So therefore it's moles per litre, moles per litre, moles per litre. So I take these three figures now back to Kc, and I'm told that it is the I2 and the H2 multiplied by one another. So 0.1 by 0.1. So it's only those figures that go into the Kc, only the equilibrium figures, over the concentration of hydrogen iodide squared, which is 0.8 to be squared. And again, get your trusty calculator, turn on your fraction. You've got 0.1 squared, because 0.1 by 0.1 is 0.1 squared, over 0.8 squared. And that comes out as 1/64. And that's perfectly fine to leave it like that. If you want to put it into decimal form, press your SD, 0.0156. 0.0156. Okay, miserable progress. Tiny Kc. Miserable progress, but that's the value we get. Now, let's think about this. If it's a case that we were asked to put units in, what would we do? Well, let's look over here first of all. That's moles per litre. That's moles per litre. And then down here, I've got moles per litre 2 times. See that? Because it's squared. And what happens here is that cancels with that one cancels with that one, and there are no units in this one. So there's no units whatsoever. The answer is simply 0.0156, or to be more precise, 1/64. Okay, now I'm going to ask you to pause the video. I'm going to ask you to read this carefully, follow exactly the same steps as I have done in the previous question, and see if you can work out what the answer to this one here is when you're asked to calculate Kc. Off you go, pause and try. Now, if you have paused this video and you've worked it out, you should have a value for Kc standing in front of you. Let's check your solution. First of all, 1 mole of ethanoic acid and 1 mole of ethanol were mixed in a container and allowed to reach equilibrium at 25 degrees Celsius. When the mixture was analysed, it was found that 0.33 moles of unreacted ethanoic acid remained, while the rest reacted to form ethyl ethanoate. Calculate the value of Kc for this reaction. Now again, I do exactly the same thing. I would write down first of all what the Kc expression is. It's the concentration of the ester, CH3COO C2H5, multiplied by the concentration of the water over the concentration of the acid multiplied by the concentration of the alcohol. So there's your Kc expression. Now, they'll always ask you to draw that, by the way, and we did that in the previous class. Now what I've got to do is to work out what are the equilibrium concentrations. Okay, so we're going to have starting concentrations, start. We're going to have changing concentrations, and then we're going to arrive at equilibrium. Okay, so again, write down your 3 species, or 4 species in this case. CH3COOH, C2H5OH, CH3, COO, C2H5, and finally H2O. Now tabulate them, just form a table around all this. So we've got 4 species this time, 2 reactants and 2 products, and the key thing I'm looking for is this one, this line here. I'm looking for the concentrations at equilibrium, and the only way that I can get that is by looking at the starting concentrations, looking at the changing concentrations, making sure that the changing concentrations is the same as the ratio that's present in the balanced equation. And I'll demonstrate that for you now. Okay, so let's read. Let's start to fill in this table. 1 mole of ethanoic acid and 1 mole of ethanol were mixed in a container and allowed to reach equilibrium. So at the beginning, at the start, I put in 1 mole of the acid, 1 mole of the alcohol. Now, as always, when you're starting a chemical reaction, there will never be products. Okay? Is there anything then given to me about any one of these boxes that remain? Let's read on. When the mixture was analysed, now, when it was analysed, it was found that 0.33 moles of unreacted ethanoic acid remained. So in other words, once we had reached equilibrium, 0.33 moles of the acid remained. So therefore, what happened? Well, if we started with 1 and we finished with 0.33 moles, doesn't that mean that we've lost 0.67? And put the minus in, because reactants will always decrease in concentrations and products will always increase. So the pluses and minuses are important. Now we're done, because once we have the change of one species, the change of every species has exactly the same ratio as the balanced equation. And if you notice in the balanced equation, it's all 1 is to 1 is to 1 is to 1. And that's beautiful, because that simply means then that they'll all be 0.67. However, the reactants will be minus 0.67 and the products will be plus 0.67. So therefore, moving down each column to work out the equilibrium concentrations, I'm going to get here 0.33 again, here 0.67, here 0.67. And just before I move on, check, does it mention the volume of the container? And the answer is no. It simply says they were mixed in a container. So we don't need to worry about whether this container is going to affect my Kc value. It's not. For the very simple reason, I suppose, as well, number of volumes are the same on both sides. Okay, so if it doesn't give you the size of the container, just take these as being moles per litre. Moles per litre, moles per litre, and moles per litre. So what do I do with them? I put all those directly into the Kc expression. So therefore Kc will come out as the ester concentration multiplied by the water concentration. That's these two. So that's 0.67 squared over the acid concentration at equilibrium by the alcohol concentration, which is 0.33 squared. And again, turn to your trusty calculator. Turn your fraction. 0.67 squared divided by 0.33 squared, this time comes out as 4.122. 0.122, which does favour the products of the forward reaction. So now we know that there's progress here, that there's a favour towards the products of this reaction. Units, well, moles per litre is twice on top, moles per litre is twice on the bottom. Units cancel. There are no units left in this question. That's it. Okay, good. Hopefully you got that answer. If not, go back and try it again and make sure that you get 4.122 as your value for Kc. Now, small little change here in this one. And it is, as you'll notice straight away, a mixture of 27 grams of ethanoic acid and 20.7 grams of ethanol. So now instead of giving you the moles, they're giving you grams. But you should go right back to the start of the chapter on moles in 5th year. That the only value that's of any use to chemists for comparison reasons is the mole. So therefore 27 grams of ethanoic acid and 20.7 grams of ethanol are of no use to me unless I convert them to moles first. So they were allowed to come to equilibrium at a certain temperature. It was found by experiment that 9 grams of ethanoic acid were present in the equilibrium mixture. The reaction is as follows. Write the equilibrium constant expression Kc for this reaction. Well, allow me to do that first, because that's always the nice easy thing to do. It's the concentration of the ester multiplied by the concentration of water over the concentration of the acid multiplied by the concentration of the alcohol. Okay, so there's your Kc expression. Now your job is to mathematically work out what the concentrations of each one of these species are at equilibrium and shove them back in. Number 2, state how you would experimentally determine the amount of ethanoic acid present in the equilibrium mixture. Now I told you at the start of this video, if you ever want to work out the amount or the concentration of any species at equilibrium, do so by titration. You're going to titrate ethanoic acid by, obviously, standardized NaOH, because that's the base we use when we're doing titrations. You could also use standardized sodium carbonate as well if you wish, because that's a base. Either one of those, but the answer there is state how you would experimentally determine the amount of ethanoic acid present in the equilibrium mixture by titration. That's the key thing. And lastly then, calculate the equilibrium constant Kc. Now again, the same three things as before. We have CH3 COOH as one of my reactants, C2H5OH as my second reactant, CH3COO C2H5 as my first product, and H2O as my second product. There will be a starting concentration, there will be a change in concentration, and then we will arrive at what we call equilibrium. And that is the line that will contain the magic numbers to go into Kc. Okay, so let's begin. A mixture of 27 grams of ethanoic acid. Problem: I can't put 27 grams in here, although let's put it in for the moment. 27 grams and 20.7 grams of the alcohol was allowed to come to equilibrium at a certain temperature, and it was found by experiment that 9 grams of the acid were present in the equilibrium mixture. So we're down to the third line, and this is 9 grams. The reaction isn't until we go to calculate Kc. Now, these three figures that they've given me are in grams. I can't use them. The only thing I'm allowed to use in chemistry for comparison reasons and calculation reasons is the mole. So I'm going to take 27 and I'm going to divide it by the molecular mass of CH3COOH. That's 24, 25, 28, and 28 and 32 is 60. So I'm going to divide that by 60. So 27 divided by 60 comes out as 0.45 moles. So we are not going to use the mass. Okay, take the next one. We're going to divide 20.7 by the mass of the alcohol. 24, 25, 30, 46. You can get that from your periodic table. So 20.7 divided by 46, lo and behold, is the same starting number of moles. So we're not going to use that. And lastly then, I want to turn my 9 grams into moles. And again, I'm going to divide that by 60 because it belongs to the ethanoic acid. And 9 divided by 60 is the same as 3 over 20, which is 0.15. Okay, so we're not going to use the grams. That's out of the question, that's out of the question, and that's out of the question. We turn them into moles first, and then we carry on with the question in exactly the same way. Okay, now let's take the first column. If I start with 0.45 moles, and I'm reduced down to 0.15 at equilibrium, that means I have lost 0.3 moles. That's very simple maths. Okay, now the change has to have the same ratio as the balanced equation, which by the way is up here, which is 1 is to 1 is to 1 is to 1. So therefore on the change line they're all going to be 0.3 because they're all 1 is to 1 is to 1. However, the two reactants will decrease by 0.3 and the two products will increase by 0.3. That's a naught and that's a naught. Okay, so that's what we end up with. So you've got your 0.45 becoming 0.15. You've got here the same thing. 0.45 minus 0.3 is 0.15. Over here, when I go down this column, it's 0.3, and this one here is 0.3. And they are the figures that go into equilibrium constant. Now just check. Any mention of the size of the container before I put them into Kc? Do I need to adjust them, or are they already in moles per litre? Well, there's no mention of the size of the container. So you can take it, be moles per litre. Moles per litre. And all I've got to do now, same thing as before, throw the values into Kc, and there's your Kc expression up here. So it's the two products multiplied by one another, which is 0.3 squared, because 0.3 by 0.3 is obviously 0.3 squared, over 0.15 squared. And again, don't take any guesses, use your calculator, trusty calculator. 0.3 squared divided by 0.15 squared, and that comes out as 4. Now, any units? Well, moles per litre is twice in the top, moles per litre twice in the bottom, no units. And again, what do we know about the size of Kc? It favours products. So therefore, we're getting good movement in this equation towards the right-hand side, towards the products. Okay, your job again now is to pause, and this time again, using masses to start off, I want you to follow the previous example and work your way down through this question here, which is on your workbook. It's question 17.10 on page 51. So off you go, pause and try and come back for the solution. If you've worked it out and you've got the answer, let's compare your answer to the answer I'm going to get here. So first of all, write the equilibrium constant expression for this reaction. So the first thing we do is write down our Kc. Now you check yours to mine. It's the concentration of SO3 multiplied by the concentration of nitrogen monoxide over the concentration of sulfur dioxide multiplied by the concentration of nitrogen dioxide. So there's your Kc. Okay. Now, when 7.68 grams of sulfur dioxide and 4.6 grams of nitrogen dioxide were heated together in a closed vessel at a certain high temperature, it was found that at equilibrium 4.8 grams of sulfur trioxide were present. Calculate the equilibrium constant Kc for this reaction at that temperature. Okay, so the first thing we do is we realize the table is a three-stage process. There's a starting concentration, there's a change in concentration as we move towards equilibrium. So therefore, that is the line I'm looking for. Okay. Now, what are my species in this system? Well, we start off with SO2, then we've got NO2, then we've got SO3 and NO. And what's my starting quantities? Well, 7.68 of sulfur dioxide. Let's just put it in for the moment. 7.68 grams and 4.6 grams of nitrogen dioxide. And then we're told at equilibrium, so we're down to this line, at equilibrium 4.8 grams of sulfur trioxide were present. So 4.8 grams of sulfur trioxide were present. Now that's filling in what I'm given. Okay, here's what I also know. The only thing present at the start of any chemical reaction are the reactants. There will never be products at the start. Okay, so therefore, let's look at this column here. Notice that we're going from nothing up to 4.8 grams. Grams, again, are not the way the chemists do business. It's not our currency. So we've got to go to the foreign exchange and change these things in for moles. So the first thing I'm going to do is divide each of the grams by the respective molecular mass. Sulfur dioxide is 32 and 32, which is 64. Nitrogen dioxide is 14 plus 32, which is 46. And sulfur trioxide is 32 plus 16 three times, which is 48, and that comes out as 80. So let's change those into moles first of all. 7.68 divided by 64 comes out as 0.12. Okay, so we're not going to use that. 4.6 over 46, 0.1. Not going to use grams. And lastly, 4.8 divided by 80 comes out as 0.06. And we ain't going to use the grams. So we've transferred to moles. Now we do the rest. The only column that I can fill in straight away is the SO3 one. If I start with no SO3 and move towards 0.06 moles per litre present at equilibrium, that means I have gained 0.06 moles in the process. The change, the ratio of change follows the ratio of the balanced equation. 1 is to 1 is to 1 is to 1. So that means That's going to be 0.06 made, and both of the reactants are going to decrease by 0.06. Okay, so now all I've got to do, oops, sorry, that's my big mistake there, put them in the wrong line. Erase, get rid of that, get rid of that. So you need to focus on these things. Okay, put them in the right place. What did I say? They're all going to be, that's 0.06 there, this is minus 0.06 here, and minus 0.06. That's the change as we move towards equilibrium. Well, let's go down the columns. 0.12 minus 0.06 is 0.06. Okay. 0.1 minus 0.06 is 0.04. And then finally over here, we've got again 0.06. Now, when you write down your concentrations in the equilibrium, check the size of the container. No mention of a container, then you can take it as moles per litre, moles per litre, moles per litre, moles per litre. What do I do with these? I fill them into the Kc expression. So therefore Kc for this reaction is going to be 0.06 multiplied by 0.06, which is squared, over 0.06 multiplied by 0.04. Now always look for shortcuts in maths. Look, 0.06 goes with one of the 0.06's on top. So the only thing then I've got to do is divide 6 by 4 and to get 1.5. And again, no units. Moles per litre is twice on the top, moles per litre is twice on the bottom. There are no units. What do I notice about a value of 1.5? It kind of slightly favours the products. Okay, so it slightly favours. It's progressing well into the product side at this stage. Okay, so I hope you got the same answer. Now, the final tweak is when the size of the container has to be taken into consideration. Okay, so this is my final example now before I give you some to do based on the same three changes in the question that we've just looked at. So consider the following reversible chemical reaction. Nitrogen and hydrogen give ammonia, where the change in heat is minus 92.4 kilojoules, and that means that this is the forward reaction is an exothermic reaction. Okay, in an experiment, 6 moles of nitrogen and 18 moles of hydrogen were mixed and allowed to come to equilibrium in a sealed 5-litre vessel at a certain temperature. It was found that there were 6 moles of ammonia in the equilibrium mixture. Write the Kc expression and then calculate the value of Kc at this temperature. Okay, well let's write down first of all the Kc expression. The Kc expression is the concentration of ammonia squared over the concentration of nitrogen multiplied by the concentration of hydrogen to be cubed. All right, now that's what we're going to fill our equilibrium figures into when we have them. So let's build our table. Starting concentrations, change in our concentrations as we move towards equilibrium. Okay, so what are the species now? We've got a species of N2, H2 and NH3. So they're the species I'm going to use, and then I'm going to try and move towards equilibrium and see what my concentrations are at equilibrium. Okay, let's start again. 6 moles of nitrogen and 18 moles of hydrogen were mixed and allowed to come. So that's the start. So what am I starting with? And I'm starting with moles, which is lovely. 6 moles of nitrogen and 18 moles of hydrogen were mixed. So therefore there was no product at the start. Okay, and then we were told it was found that there were 6 moles of ammonia in the equilibrium mixture. So down on this line there were 6 moles of ammonia. Okay, now here's the key thing. We now know that with the ammonia column, the change that I can fill in here is from 0 to 6. So therefore there was a gaining of 6 moles. All right, now here's what I need you to be careful with. Because the ratio of change for the rest of them has to be the same as the ratio in the balanced equation. So for example, let's take ammonia to nitrogen. Ammonia to nitrogen is 2:1. So therefore this also in the change line has to be 2:1, which means we have it. And because it's a reactant, it's being used up. So 6:3 and it's -3 because it's being used up. Okay, and then we can see that the ratio between nitrogen and hydrogen is 1:3. So therefore the same ratio has to be down here. 1:3 is the same as 3 is to 9. See that? And then we finish the columns. 6 minus 3 gives 3. 18 minus 9 gives 9. And 0 plus 6 gives 6. But pause. Because this is equilibrium in a 5-litre vessel. So these are not concentrations in moles per litre. These are concentration in moles per 5 litres. So what I have to do is I've got to divide them all by 5 in order to get the concentration now in moles per litre. And once I've done that, I can then fill these concentrations into Kc as follows. We have 6 over 5 to the power of 2 divided by 3 over 5, which is the concentration of nitrogen at equilibrium, multiplied by 9 over 5, which is the concentration of hydrogen, raised to the power of 3. Now, please make sure you get your calculator to do this and take your time with it. Turn on your fraction, and the first is 6 over 5 raised to the power of 2. Multiplied by, on the bottom line, fraction with a bracket, 3 over 5. Close your bracket and open your bracket again. Fraction 9 over 5. So all you've got to do is basically build that fraction there, that Kc fraction, build it on the screen of your calculator, raise to the power of 3. And when I press equals, I get an answer of 0.411. Now, let's check moles per litre. Let's check units. Moles per litre is present twice on the top, and moles per litre is present 4 times on the bottom. So therefore, there will be an excess of moles per litre squared on the bottom. Moles per litre squared on the bottom, and they are the units you would use for that corresponding value of Kc. Okay, look, play these as often as you want. Go over them time and time again. If you have questions, you have my email. Please do get back to me. Don't suffer in silence and think that you have to wait until our live class. You don't. Send me an email and I'll see if I can help you through it. But we might even organise a little live class ourselves and see how we get on. But what I want you to do now is, having gone through those and the 2 examples you've done yourself, I now want you to go through these questions here. There's 3 of them, but I want you to go through them. And again, you'll notice the first one is quite simple. It's given to you in moles in a 1 litre vessel. The second one is given in terms of grams, okay, and doesn't mention the size of the container. And the last one then is also given in terms of grams, but it does mention the size of the container. So you can stop this video now. You can work on those 3 questions, and then at the start of the next class, I will come back with the solutions of those 3 questions to you.